There we go. Cool. So this is going to be the first of a workshop series about reverse engineering. So today is mostly to cover a syllabus of sorts, mostly to cover what topics that I'm going to go over during the duration of this, and some of the expectations that I have for either what you'll learn or what I expect for you to have before or coming into this. So to begin, why is any of this even useful? Get out. I don't need you anymore. So why is this any useful? I think it's pretty fun. It's like solving a series of small puzzles that build upon knowledge from several areas. So you might need something from cryptography, something from math, something from programming, something from assembly, and so on. So there are a lot of different areas that start to feed into reversing. So it's like an intricate puzzle that requires a lot of knowledge going into it, but can be very rewarding coming out of it. Very useful for debugging applications. So there was someone in data structures that I was helping for an assignment.
Tyler.
Yeah, and I amazed them by showing them what section of code their set fault was occurring in, because they thought set faults were just magic, and there was no way to figure out what was happening. So through GDB and some other tools, I was able to figure out what section of code and then look at it to see what was actually causing the issue. So very useful for debugging and so on. Can be very useful for figuring out how something was developed. There are countless times where I see a binary come out, but there's no source code. So I will sometimes go through the binary to see how did they actually get this done and what types of tools they may have utilized and so on. So it's very useful for figuring out how things were done and to learn a little bit from it. It gives you access to the aspect of trying to exploit something at a binary level. And I say gives access because the exploitation part is a whole nother level of difficulty. But a lot of the reverse engineering tactics that you would utilize are necessary in order to get to this level of exploitation. And then pay ranges. Reverse engineers, security engineers doing this type of stuff make quite a bit of money. My starting salary is in the 80K-ish range, so.
Only?
Anyways, so some of the topics that we're going to go into. So this would be like my intro, lower level understanding. So some of the things that I expect you to build upon in order to understand the higher level concepts. So we're going to go into binary. From a show of hands, how many people know binary already? So a few people don't. But that's okay. It's very simple to grasp and go over. So definitely going to focus on that first. And with that, it's helpful for understanding how a CPU works. And topics within binary, we'll be going over our binary arithmetic. So we actually don't do any subtractions, pretty much all addition. Going over OR gates, AND gates, XORs, and truth tables. 1 and 2's complement. And then Indianness, because Indianness is very important, especially later on. Afterwards, we'll go into hex. So hex is like an intermediary after binary. Hex is supposed to be human readable, and a lot of people may think, well, this really isn't that human readable, but it's better than looking at ones and zeros. So it's there in essence to help the programmer, to help the reverse engineer, to help whoever's working with it to understand what's happening without having to go into bits. So definitely useful for reverse engineering when loading values into memory and so on. And you don't really need to memorize any hex. It's nice to know as a concept. There are a few hex values that I will expect you to know, but otherwise it's not really necessary to memorize per se. But it has been very useful. I had a challenge that I worked on during some clinic where I was reversing ASCII to hex, and it's been stuck in my head ever since. I find it very useful for certain things. We'll cover octal, but mostly for fun. I guess it helps with file permissions, but there was one professor who told me one use case other than file permissions that octal was useful for, and I can't remember it. But there are fairly few reasons as to why octal is useful. We will cover logic gates because there was another professor of mine who covered them, and through logic gates, you gain understanding into like overflow, carry flags, and so on. And the aspect of knowing the implementation at a CPU level is definitely helpful for understanding how these flags are set, and it gives you a, I'd say, physical representation as to how these things work. So it's very useful in my opinion, and helped me with a lot of my understanding of them. To continue, we'll go into a little bit of crypto and basic math. I'm not expecting anything like above algebra for my math, but some type of math skills are things that we'll cover. So a little bit of encryption with maybe ROT, Caesar cipher, and XOR, because XOR is utilized a lot in these types of reversing technologies. For instance, XOR is used in like one-time pad. I believe it's used in pretty much every encryption medium right now. So XOR is very useful to understand at a lower level, and how it's useful for crypto. We'll go into some C and then systols with C. So we're going to cover C programming at a very low level, not at a systems level, but just at a here's a C program, here's how some of the stuff works, how the flow works. We'll go into some insecurities with C, and then we'll look at compiling those and seeing how they are represented at a assembly level. Then we'll go into some Python programming. Find Python to be very useful for its libraries and reversing and exploitation. So it'll be very good for automating that type of stuff. And also a lot of tools that are written in Python that use some type of Python that are useful for reversing or finding anomalies. Now we're going to the intermediate topics that I'd like to cover. So we're going to cover Intel and AT&T x86 assembly. So these are two different types, but honestly, they're very close. Intel being for Windows, AT&T being for Linux. So we'll cover that in a second. So 32-bit is, or x86 relates to 32-bit assembly, and so definitely necessary for reverse engineering anything that's 32-bit. It's one of the most common instructions, or the bit architectures for CTF challenges, mostly because any tool that you want to reverse engineer 64-bit binaries or so on, that you want to do static analysis with, usually costs upwards of $1,000. So there are some other tools that will use the free versions, but paid versions can go up to $10,000. So 64-bit's a little bit harder in that respect, but there are still some other ways that we can get around that we can use to reverse engineer those as well. So 64-bit really just, in essence, the difference is that the people who made the chip architecture and so on went towards more of a reduced instruction set and added a few more registers. So really the only difference between 32-bit and 64-bit. There's a little bit of a difference in memory access, but we'll cover that when we're talking over those topics. Then we'll go over some demos of ARM, PowerPC, and MIPS. I've done a little bit of work with MIPS, a little bit of work with ARM and PowerPC, but they're not the most common. So ARM, PowerPC, and MIPS are going to be used in like smaller devices. So I believe all of your phones are probably going to operate under ARM. A lot of phones and so on operate under MIPS. And I'm trying to think. I think PlayStation 4 and most of the PlayStation devices operate under PowerPC. So if you ever want to do some reverse engineering or exploitation of PlayStation, PowerPC might be useful. But
really old Mac.
yeah, pretty much. So those will be covered mostly for fun, and we'll go over some of the differences in the instruction sets. So we're going to go into some of the differences between Intel and AT&T real quick. So the Intel syntax is for Windows machines. So for the format of instruction, it's the instruction followed by the source to the destination. So if you're moving something, for instance, so if you wanted to move something from one register to another register, you'd move it from the source to the destination. The difference is in AT&T syntax, which is for Linux machines, we have source and then destination. So the source is on the right and destination is on the left. This honestly confuses a lot of people towards the beginning because understanding which way the data is flowing, and we will be doing some reversing of Windows binaries as well as Linux binaries. Formerly, I've been taught with Windows binaries, but most of my experience is with Linux binaries. So I can definitely mix it up with both of these types of things. Another thing for the Intel side, byte size depends upon registers, so it's a little bit ambiguous. One of the reasons I don't really like Intel that much. And AT&T, you have some type of intermediary on the instruction, so you're either moving a long or moving a byte or moving a word or something. So it dictates the size on the instruction itself, which is really nice in my opinion. So now to continue some of the intermediary topics. We're going to go over tools for like footprinting and image analysis. And I say image analysis, but it's not going to be like a image in like an operating system image, but like actually taking an image of data per se. But we'll cover that a little bit more later. A professor that I had,
Sorry.
time to pull a Clark.
Huh?
Time to pull a Clark and lecture for the next 10 minutes on why people showing up late are wasting your money. Actually, you're not paying for this.
I was too busy eating, and then I looked at my computer.
It's all good, it's all good.
What did I miss?
You've missed the beginner stuff and some of the intermediate, but basically we covered that we're going to talk about binary, hex, and assembly. Okay, so continuing on, Footprint's a tool that a professor of mine made, as well as a few other tools that he made for Windows analysis, so they're very useful for the forensic side of figuring out what files were changed and so on to your file system. So very useful for that. We'll also create a Python tool which takes an MD5 sum and will check changes similar to how tripwire works. And if you took Merit's attack and defense class, it's a tool that he made, or that we made during that class that's very similar to that. We'll cover some Wireshark, so this is useful for network analysis and to track data coming out of your machine. So not every person who does something malicious is going to be smart and try to encrypt the data that they're trying to exfiltrate out. So if no encryption is occurring on this, then we'd be able to see what type of data is being exfiltrated out of your machine. And through this, I might develop some sample malware-esque binaries for you to run on your systems. And then I would like you to track and document what types of things you found and what types of things you might have seen. And we'll go over some stuff, some methodologies for how you would find out, per se, what port the binary is running on and so on. And some of those tools would be like strace and ltrace. So strace is going to be your syscall trace and allows for our analysis of syscalls, so you'll be able to see what system utilities are being called and what values are being passed to them. So if you're doing a read or write, or if you're opening up a socket on a port, you'll be able to see that type of stuff. So strace can be very useful for that. A lot of strace can also be used, like, so say you're doing a string copy, and string compare, and you're comparing something in memory or something written to the file. Strace will allow you to see what values are being compared. So if all you're doing in your to check a password per se on your program that you've written is just doing a string compare with regular data, I can pull that from memory or I can pull that from the file and easily find the password that you're utilizing. So one aspect to not use string compare for those types of utilities. Library trace or ltrace just tracks the libraries that are being called. This can be useful for going into and trying to find exploits or maybe libraries that are older that may have something vulnerable with them to try to take advantage of the binary. But that's a little bit more of a corner case that we made over. GDB is going to be the new debugger, very useful for debugging things on a Linux operating system. And we will go over some things that make GDB a little bit nicer, because GDB at its base level is really terrible, in my opinion. Now some of the advanced topics. So right after covering GDB, we'll also go into some disassemblers. So this is topic or a somewhat small list, just some of the disassemblers that are out there. So object dump is just a command line utility on Linux that allow you to dump the assembly of a binary. IDA is going to be your static and dynamic analysis for Windows. So it allows you to do some, let's talk over the concept. So static analysis is going to be, you have the data and you're just viewing the instructions and going through to see the type of flow that is occurring within the file. Dynamic analysis is actually running the binary or the tool and then seeing what's happening by examining the runtime and the memory of the tool that you're analyzing. So IDA will work for static analysis of any binary, but dynamic analysis will only work on Windows. It has a way that it can tie into GDB, but it's super terrible. I don't recommend it. Binary Ninja is a tool that I really like. It's a static analysis tool, actually written by some people that used to work at the company that I worked at over the summer. So some really cool guys. But they have a free version that you can download from GitHub and install from source, which allows you to do static analysis. And it is one of the nicer looking static analysis tools out there. So I would highly recommend using that one for your static analysis. It also gives you better flow diagrams, and we'll see what that really means later on. WinDebug is going to be for static and dynamic analysis of Windows tools. WinDebug is probably one of the better ones because it's actually made by Windows, I believe. And it gives you a lot of tools for reversing or trying to figure stuff out with like operating system level stuff in Windows. So if you wanted to load a module per se into it, then that would be something that you'd want to do. OllyDebug has a really nice interface and is nicer than IDA in my opinion. But if you want to load big things in, if you want to do something that's a little bit more complicated with Windows, it's going to fail, and it's going to fail hard. So WinDebug would probably be the best one for debugging if you're doing purely Windows side. For the Linux side, you're going to have GDB, Binary Ninja, and then PETA. So PETA is the Python Exploit Development Assistance for GDB. And really what it's doing is it adds some Python usefulness to GDB. Also edits the GDB init file to add some niceties per se. It's also great for looking at a dynamic analysis and some snapshots of memory. So PETA's, or GDB PETA, is what I commonly use for my reverse engineering of Linux binaries. PwnTools and PwnLib, so these are going to be libraries underneath Python. So these will be things like an advanced topic that we'll talk about after learning Python, or at least getting everybody up to speed with Python. And they allow for automation of reversing and exploitation of binaries. And we'll cover some aspects where I've written tools using PwnLib and where other people have written tools using PwnLib to do like CTF challenges and so on. So now we're going to go into some of the expectations that I kind of have for this. So I'm assuming that most people have some type of access to a computer, mostly for obvious reasons. You're going to be doing some type of reversing of a binary when I give the challenges out to you. So having access to a computer would be nice. You don't have to bring it to the workshop lectures, but having access to one like at home would be nice. Some type of VMware experience or the ability to learn. So realistically, I want you to have access to a Linux and Windows VM. This is because, one second. This is because I may give you something that may be malicious, and I don't want you to run this on your live system. So for obvious reasons, you would want to VM this. And I promise I won't do anything where I try to do VMware breakdown to try to actually infect your host system. But yeah, some of the stuff that I send over Slack may have something which does like exfiltration of your shadow file, or does exfiltration of like maybe what tools on your system are executable as root, and so on. So some type of information gathering that will exfiltrate data out. So I wouldn't want you to actually have a system that you actively use that you run this on, because I don't want to actually get your data. I just want to show you what one might look like. I also expect some type of basic Linux experience or the ability to learn. I'm not expecting you to be a Linux guru per se, but like being able to run an application from the terminal would be useful, and being able to install something from source would be useful. And whenever you're installing something from source, and all right, whoops, and we're back. Cool. So yeah, whenever you're installing something from source, there's usually a very good guide online on how to install it from source on the operating system that you're using. So it's not really that difficult, but the ability to try to do such would be nice. So access to Slack. I'm going to develop a private Slack channel, so if everybody could at the end just give me your email so that I can add you to this private Slack channel, and that is what I'm going to use to distribute the binaries or like homework assignments that I'll be giving out, and sharing maybe like online resources, or if you're looking for help on one of the challenges or info or whatever. So there will be a private Slack channel created for this, so if I could get an email from everyone, that would be great. The ability to work on your reverse engineering projects at home. So I will cover and I will solve the challenges that I give you, maybe 1 or 2 weeks after I give them out. But I do expect you to do some type of work on them, because I'm not going to cover everything per se during the solving. I will just cover the high points, because we need to get time into the other concepts that we want to cover. So these will act as your homework per se, and solutions will be posted, or I'll do them in class. And then some proficiency with math. I'm not expecting you to have Cal 1, Cal 2 level math, but being able to do calculations of power of 2 and power of 16. The power of 16 you could probably use a calculator for, but power of 2 is probably useful to understand in your head. And the ability to learn from various mathematical or mathematics-related cryptography topics. So that's the end of my slides for the moment. We're only 25 minutes in, so let's cover some binary for the fun of it. So how many people know binary, or how many people don't know binary currently? So about 2 people? Cool. So let's just cover these topics. Cool. So we have these things that I want to call bases. So when you talk about 0 through 1, 2, all the way up to 9, this would be your base 10. This is the number system that we commonly utilize because we have 10 fingers, right? So we go from 0 to 9, and then we bump up to doing like 10 or 100 or so on. So we increment the amount of values, and pretty much everything's going to do something similar. So that's base 10. So binary is going to be base 2. And we only have 2 values for that, 0 and 1. So we see that over here, when you move into a new place, so we have 0 through 9 here, we'd have 0 through 9 here in base 10, right? But we're multiplying this one by 10. So in binary, we have something similar. So we have all of our places. And we have 2 to 0. So what is 2 to 0? 1. 1. We have 2 to the 1. 2. 2 to the 2. 4. 2 to the 3. 8. 2 to the 4. 16. 2 to the 5. 32. 2 to the 6, 64, and then 2 to the 7 of 1, 2, 8. So that's pretty easy, right? And we can keep going on. Some notable ones that you might want to know. 2 to the power of 10, this is 1024, or effectively 1K, or 1K of memory, 1K of bytes, and so on.
2 to the 16.
Well, I know 64K, but we'll just cover that for right now. So that's your basic understanding of it. So if you wanted to have a number that's well, actually, let's have a little challenge here. What number is this? Well, it depends. Is this signed or is it unsigned? So we haven't talked about that yet, but we have these differences called signed and unsigned. So in a signed bit per se, you would have your most significant bit as your signed bit. The most significant bit being the highest addressable bit for the register. So if we're saying our register is 8 bytes, or 8 bits per se, then our most significant bit would be here. So if we were unsigned, you're saying it's what?
It's got to be positive one.
So if it's unsigned, it's going to be positive, right? Because you don't have negatives in unsigned.
Mm-hmm.
So these are always going to be positive. This one could be positive or negative. All right, so what's our unsigned value of this? And let's give it in hex.
Four, 8, 4.
So 0xcc. Is it cc or dd? I think it's dd. All right, so we haven't really covered hex. So let's get the integer value here.
I know 1111 is that.
So this is 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5, 2 to the 6, and 2 to the 7. So we're taking 2 to the 7th plus 2 to the 6th plus 2 to the 3 plus 2 to the 2. What is this going to equal?
60 plus.
All right, math is hard.
It's too early for this. 4 is 8 to 12.
So we have 1, 2, 4, 8, 16, 32, 64, 128.
Okay.
So we're taking 128 plus 64.
Plus 8 plus 4.
So if we align these up,
2.
and we get 204, is that what we're getting?
Yes.
Okay. So, as we can see from this, the conversion from binary to decimal is annoying and not very fun. So now let's try to convert this to hex. But let's go over what hex is. So we're going to keep this number up here. Where did I put my... And we're not going to cover what it is unsigned because right now. But let's cover what it is in hex first. So hex is going to start with 0, 1, 2. It's going to continue on to 8, 9. Then we do A, B, C, D, E, and F.
So B.
So this is value 12, right? So that's 8 plus 4. So 9, 10, 11, 12. So C. So it actually applies both ways. So this character in hex is also the same character over here, but we have another place. So we have 0xcc, but this one is multiplied by 16 to the power of 0. This one's multiplied by 16 to the power of 1. So again, we have a similar type of multiplication by the base. Now, does anybody know what this instruction does in assembly, by chance?
It's the error.
It's a software interrupt. And this is one of the ones that I might expect you to remember. Another one that I want you to remember is 0x90. Everybody know what 0x90 is?
No.
No op. What is a no op?
Does nothing.
Yes, no operation. So of the 2 things that I probably want you to know, or I'd say 3 things. So these 2. And there's one other value that I want you to know, which is 0x41. Anybody know what that is?
A.
Yep, capital A in ASCII. So if you're doing a hex to ASCII chart, 0x41 correlates to A. So sometimes when you're putting in inputs, I recommend putting in a bunch of capital A's. And then you would look for any thing in memory, which is a series of 0x41, 41, 41, right? So it's a easy identifier, and the only reason you want to learn anything for ASCII for this purpose, I'd say. Alright, so we've covered unsigned arithmetic. Well, let's go back to signed arithmetic. And we'll assume 2's complement here. But now we need to go over what 1's complement is. So with 1's complement, you're inverting the bits. So you get the value of this, but then throw a negative on it, like if you want to do it in decimal. First, you would invert all of these bits. So 0, 0, 1, 1, 0, 0, 1, 1. So this would be 1's complement. And all we do when we do 2's complement is we add 1. So when we add 1 in binary arithmetic, this one becomes 0, we carry the 1. This one becomes 0, we carry the 1. So that's 1, 0, 1, 1, 0, 0. So this is going to be 0, 1, 2, or sorry, 1, 2, 4. So 4 plus 16 plus 32. So 52, so this is negative 52. After this was unsigned. Is anybody confused about this? So this is a little bit of a important topic. So does anybody want me to go into this a little bit more that hasn't covered 2's complement before, or 2's and 1's complement?
So the top value, the very top one is negative 52?
Yes, this is negative 52 in 2's complement. But to convert it to a way that you can read it, yes.
So if you see a string of ones and zeros,
Yes.
so let's say there are 8 bits, then how do you, so when the how is it stored in the processor like x86? Is it?
So x86, you're going to assume that you have 32-bit registers. So that would mean that the 32nd bit, so the bit all the way on the left, the most significant bit, is going to be your signed integer. Now, we haven't gotten into logic gates yet, but in essence, it does, at a CPU level, it doesn't care if there's a 1 here. Because what it does is through the logic gates, as it's traversing through them, it always sets the overflow and the sign flag. It is up to the programmer or up to the assembly language to say if it wants to do anything with those flags. So these flags, or like sign flag, they're always going to be set, but it's up to the user as to how they interpret them.
Okay, so if the user doesn't set anything, let's say he just declares a variable and he stores the value of whatever it is.
Yes.
So if he hasn't declared the sign for that particular variable, I assume it's unsigned.
If it's, no. So if you're doing something in C, so let's say you're doing something in C. If you assign integer 6, or int a equals 6, right? The fact that you're assigning to a int means that you're doing something signed. It'd be, I think it's uint or u underscore int, something like that, for an unsigned integer. So technically, you're always doing something like that at a C level. Now, at an assembler level, these things are always going to be set. So the register doesn't care. But it depends on the instruction that you use that then correlates to whether or not you care about it. So there are comparisons where you can compare the if it's equal to or if it's not equal and so on. And there are different types of instructions that you have in both, I think x86 and 64 have the same instructions, but the instructions themselves then correlate to whether it's signed or unsigned arithmetic.
Okay, so just to build up on that, so you said like in C, let us declare a variable a equals 6, like so unless a program, so if it's a int a equals 6,
Yes.
so in that case, how would x86 store it? Because I'm confused. I understand the two's complementary, but I'm confused how it's stored.
It shouldn't store it no matter what. So you would move, and we'll say we're doing AT&T syntax here. So we would move L, we're going to store it in EAX, and we're just moving, I think it's $, or we wanted to do 6, right? So you do $6 here. So this would move the integer here into EAX. So when it's stored in the register, it doesn't care. Now when you do your compare, or if you want to, the jumps, so you have like JE or JZ and so on, when you're doing some type of comparison or some type of jump on the comparison, that's when it checks to see, does the programmer care if it's signed or unsigned? Does that make sense?
Kind of. But
So-
I might come back to you on that.
Okay. As far as storage is concerned, the architecture doesn't care. It stores it as it is.
By store you mean storing a registers, right?
Yes,
Not
it's
like
storing
writing
within a
it.
register. But if it wrote it to the file, which a lot of times when you have it like that, it would write it out to the file possibly. It would store it as a bit. So when you're assuming int a equals -2, then it's going to do the calculation of what -2 is to figure out what it is.
So
Right.
It's going to store the 2's complement of it.
Yes.
It's going to calculate the 2's complement of 2 and store that
Mm-hmm.
when you put a minus on it.
Yes. So that's happening at the compiler and assembly level, though.
Okay, so it's safe to assume that whenever you declare a variable without a sign,
Yes.
it's stored as it is. And if there's a sign, then
Mhm.
it's calculated the 2's complement and stored in the
Yes. However, what if you go over? So an integer is either going to be 4 bytes or 8 bytes, depending upon what computer you're using. So like my MacBook is 8 bytes for an integer. Most Intel or most computers like Windows side are going to be 4 bytes currently. 64-bit might change it to 8 bytes. There are a lot of considerations here, but so let's assume 4 bytes. Then we have 32 bits. So if we're doing anything, we can't store a value here which is larger than what the 32th bit can store. So it's going to be 2 to the n, and I think it's minus 1 because of the 2's complement. So with 32-bit, I think this is n minus 1 as well. So we would take 2 to the 31 and then subtract 1 for it. That would be the maximum value that we can have stored within that register or within that value. So it depends on the data type as well. But if we only have 32 bits for the register, then we assume that anything that goes into the most significant bit, or that 32nd bit, would entail that it could be signed or it could be negative. So if you wanted to store more values or have a larger number, you could do a uint or something else like that.
But storing anything above 32 bits on a 4-bit machine or 4-byte machine, wouldn't it cause an overflow?
Technically, yes, but you have things that you can consider. You could have a long int, which would do 8 bytes. And even if you only have 32-bit registers, you could use 2 registers for that instruction then, which then gets into more complicated stuff. You had a question, Julian? Anything else? Cool. Let's see, we've covered quite a few concepts on that. Let's cover Indianness real quick. So does anybody know what Indianness is, or want to explain to me what Indianness is?
Big Indian.
Yeah. So we know that there's a little and a big Indian. So this is the byte, or let's say bit representation. We don't care about the spelling of representation there. I ran out of space.
How's this spelling?
I believe it's spelled right, but I just ran out of space.
This is S.
Oh, wow. Okay. Yeah, we're just going to erase that. I didn't record this. I totally recorded this. Never mind. Presentation. I think that's the correct spelling.
Yeah.
Cool. So we have a little and a big, right? So we have NDN, right? So if we go into how this word came about, there's a book where somebody talks about eating a sandwich, and they could eat the sandwich going by the big end in or the little end in. And so the programmers who developed these systems coined this word off of that book. So by big end in, we take the most significant bytes. With little end in, we take the lowest bytes.
Which one comes first?
Huh?
The most significant byte comes first.
Yes.
Big Indians.
And bigger than. So this would be big, this would be little. So going back to our, actually that's a bad example. Let's say 0, 1, 1, 0, 1, 0, 0, 1. So in this representation, I'm representing it as a big Indian. Because in Big Indian, it's easier to disseminate information for us. The computer really does not care. So if we were to do this to Little Indian, we would basically flip these. It would be 1 0 0 1 0 1 1 0, right? That's kind of the difference. And it's just a representation of how computers read things in. A lot of our operations go on the lower bytes, so it is more efficient to examine the lower bytes first, which is why Little Indian is the preferred methodology for most systems. But then you could have a different architecture which does Big Indian because it might have bigger numbers and so on. So it really depends. But it operates at a byte and nibble level. So this entire thing would be considered a byte, and this 4 bits would be considered a nibble. So it just flips the nibbles per se.
Does it flip it, or does it just represent it from left to right?
It represents it it reads it from here to here in Little Indian versus from here to here in Big Indian. So that's just how it reads it. And it technically represents it that way as well. So it's flipped in our minds, but that's just how it reads it in. Yes. Any other questions? Let's go into not logic gates. Let's go into truth tables. So for those of you who haven't experienced a truth table before, and how much time am I got left? Time is it? 10 minutes? Okay. So yeah.
It's 3:50 right now.
So I have enough for truth tables. So in truth tables, you have a set of bits. So over this side, this is going to be your answer or your output, and this will be your input. So we'll start off with 0 0 0 1 1 0 1 1. And let's say that we are doing an AND. So for ANDing these two values as a logical AND, what does a 0 and a 0 make? Huh? 0, right? What does a 0 and a 1 make?
0.
0, yeah. What does a 1 and a 0 make? 0. And a 1 and a 1 makes 1. So that would be your truth table for an AND. Let's try an OR. So for an OR gate, what is 0 and 0? 0. 0 and 1?
1,
1 and 0?
1,
1 and 1?
1.
Cool. Alright, now for the next one, we have something called an exclusive OR. Let's see if you guys can get this one. So in the exclusive property, we say that it has to be one or the other. So for 0, 0, 0 and 1, 1 and 0, 1 and 1,
0.
0. Yes. So that's pretty easy. Now, these are some of our fundamentals, I would say. Trying to think, is there anything else? That should be fine. So now, if we talk logic gates, let's say that I have 2 inputs. And we have some output. And let's say we have XOR occurring here. And let's say that I control this bit, but this bit is from the user. So if I'm always putting a 0 here, what does the user's bit turn into? No. Because the user could have either 0 or 1. So if I always put a 0, what's happening? Yeah, so it's whatever the input the user gives you. So it would be whatever its input. So in this case, we would have something called a pass-through. And this is some of the intermediary before we get into actual logic gates. So what if we say that we have the same situation for performing an XOR here, and we have our user bit, which should be a 1 or a 0. What am I doing now that I have a 1? So if the user puts a 1 in, what results from an XOR of a 1 and a 1?
0.
0. If it puts the 0 in, what results from the XOR of a 1 to 0? 1.
1.
So I'm inverting. This would be called an inverter. Now, we have these things called not operators, right? So I think they could be represented like that, but that's how we represented them. Is there another way that we can represent them for people who took data structures?
That's not represent.
There's another way, though. There is another way. I can't remember what it was.
Are you talking about the
above part?
That's right. You could have it above.
Bar.
Yeah, the bar above it. So there's multiple ways, but so for knotting something, so if I wanted to knot A, and A was 1, we would put 0, right? So this is a way to knot something. So now, if we're thinking about this at a CPU level, and we want to have the ability to knot something or just pass it through, we can feed everything through an XOR, and we can control whether it's being flipped or not. So this is one methodology. So if we wanted to feed this into like an adder, which would add bits, and we want to control whether it was flipped or not, then we can have an XOR and we can control the 1. And if we are inverting it, or if we're knotting the value, we can just put 1 for the value of our controlled bit for the XOR to invert the value coming in. Does that make sense? We'll cover this a little bit more in detail when we get into logic gates, which will probably be the next lecture. How much time do I have?
5 minutes.
5 minutes. You guys want to go over octal real quick?
Oh,
Actually, yeah, I did want emails, but totally forgot to take that. Yeah. Anybody have a piece of paper I have?
the sheets are this.
Did we already do this? All right, somebody was a boss. Okay, so did everybody sign this that wants to attend? Cool. So just write down your email, and I'll invite everybody to a private Slack channel. Any other questions before we get into octal? So octal's going to be very quick. We have base 8, which is octal. And for our bit values, we have 30. And they can be represented in binary. So 1, 2, and 4. And our values go from 0, 1, 2, 6, all the way up to a maximum of 7, with a total of 8 different values that we have. Does anybody know the use case for octal?
Permissions.
File permissions. All right. Does anybody know the file permissions that octal correlate to?
User group, worlds.
So read, write, next key, right?
Oh yeah.
So most significant bit for an octal number would be read, so that's 4. Write would be 2, and execute would be 1. So if you wanted to assign all permissions to a file, and then you have your 3 groups, it would be 7, 7, 7. Assigning read, write, and execute to, I believe it's user, group, and then world, or global, or everybody. However you want to determine that last one. So we have a read, write, and execute, and that's basically it for octal. Octal's really not that fancy, and the only use case that I know for octal is file permissions. Any questions on that? Okay, then I think I'm done for today.
So is this happening every week?
Yes, every Monday from 3 to 4.
Oh man, you made it perfect for my schedule.
Okay, Chris, so you said OXCC, the software interrupt.
Yes.
So is it user defined?